Essentially, G-force is a misnomer. It is acceleration, not force. So, G in itself is around and about 9.8 meters per second every second. Which, we can come on to what that means if people want. In fact, I think we should at some point. But 1G is the acceleration that you feel due to gravity on Earth. So I'm sitting here now. I'd normally use the example that you are, but I know that Andrew will start, being awkward. I'm sitting here. The Earth is pulling me towards it with that acceleration. Now, obviously, I can't move there, but there's a force involved. And the force is my mass, which is a lot, multiplied by that acceleration. That's how you get weight. So I think the old classic high school example is because G-force on the moon is about a sixth of what it is on Earth. You get sort of, you've got the same mass on both because a mass is, how much matter there is in you. But your weight will be different because your weight is a force. And again, I noticed that Andrew is doing the classic. That's got to be a copy and paste from Wikipedia, hasn't it? So yeah. So I think that's the first big thing I wanted to cover is that G-force is acceleration, 100%. Yeah, it's all right. I've got Wikipedia up as well. Don't worry. So let me know, folks. Everyone happy with the idea that 1G is, is the acceleration due to gravity on Earth, and that a force of 1G is really you feel your own mass. Hi there, Nightfall Torius. Welcome on in. Thank you very much. How are you doing? It is great to see everyone out here, by the way. I will try and mute. By the way, everyone's getting a behind-the-scenes view as well. So, we've got what G-force is, I think. Please let me know now if that doesn't make any sense to anyone. Another sort of thing there is, obviously, if you're feeling one lateral G, as in you're feeling 1G in that direction, that means you're getting accelerated in that direction by that speed. My finger's not in a good state. In that direction by that speed, well, by that acceleration, which means that you'll feel, if you're accelerating up against something that's there, let's say the edge of a roller coaster car, might as well go that one, you'll feel your whole, the equivalent of your whole weight on that side. So G-force can go in, forces and G-force can go in any direction. But in general, at rest, we have one on us heading towards the centre of the Earth. So, taking that in planet coaster terms, what you've got is, you'll notice that vertical Gs, you will see that something like a monorail or whatever is going to have one vertical G, no lateral, no acceleration. Roughly. So, here's the first thing I think I want to go into is, well, knowing that, and knowing that a lot of us are quite big into roller coasters, we quite like the feeling of a 0G hill, which is where you feel weightless. You've got no G-force acting on you. So, and the idea is that you're accelerating towards the Earth at that speed. So the Earth is pulling the 1G on you, but there's nothing stopping you from going at that speed. Close, Minx Heroes. That's not quite. It's coming on for floaty airtime. I think you've got to go slightly below 0 before you get actual airtime. But it's close. Let's have a look at what acceleration is. Let's go back a little bit. Let's actually use the pen and paper. So, in general, a graph that you would have probably seen back in the day would look something a bit like this. So, I will try and draw. I will probably fail miserably. at a straight line. And yeah, we need to adjust this camera. This was what I was worried about. Let me just quickly do some adjustments on here to make it so that you can see what's going on. Because I think I need to drop that auto exposure a little bit to there. And the focus needs to move around a little bit as well. And that looks better. That looks much more how I see it. So you'll see that. Let's label the axes. Let's say that you are time. Let's say that this is velocity. And let's say that we're accelerating. So we're going to draw a straight line. Yeah, it's not going to be straight, but sure, let's try and get it as straight as we can. So that is how someone's velocity or speed changes in time. Technically, I'm saying two different things. We'll get into that later. We'll get into that when we talk curves. We have a start and an end. Let's put the end sort of there for now. And the time. So this let's label the values in a different colour. Let's label them, let's say, in red. And not bang the mic. That would be bad. So we'll have that is t. We'll say that the starting velocity is u, because the ending velocity can then be v. And the colours aren't showing up overly well, but that is red. Now that shows up a lot worse on screen than I was hoping. We might not be doing this with many colours. So there we have a graph of time and speed and velocity. So what do we say? Well, time is measured in seconds. If my hands hold out writing out throughout this will be impressive, by the way. U and V, we're going to do it in meters per second. So that's seconds. Let's just say meters per second. And acceleration, which we're going to denote with A, because why not? Makes the most sense. That's in meters per second per second. Might as well sort of write it like that. There are more, better ways of writing it, but that will do us for now. And we might as well have S is the displacement, because for some reason it's not D. Don't ask why. No need for the jokes. And that's measured in meters. So, for an interesting idea, let's work out in terms of T, U and V what the acceleration is. Let's split this graph off kind of here. So we're only looking at that. Well, U and V are both measured in meters per second. A is measured, acceleration is meters per second per second. So that kind of gives us a hint on how we work this out. You're struggling to see the writing, Kaylee. If you're watching on a phone, I don't expect you to be able to see pretty much anything, I don't think. Unfortunately, I've zoomed this camera in as far as I can. How's everyone else for being able to see what's happening here? Hi, Frankie, how are you doing? Are you making sure to study hard? Making sure to do all your work and being a good lad? Disc can see, that's good news. So far, is everything I've sort of said made sense? Even if the letter S we're using for what is called displacement. Yeah, you can't read that properly, but hey ho. He says, yeah, and hi to Minxie Rose. Excellent. So that'd be your displacement. So if we want to move from meters per second and get to meters per second, you think it's just you, to be fair, maybe need an early eye test. Might not be a bad idea. Honestly, I don't think it's focusing particularly well. I think I'm using the wrong camera for this. And what I should do if I repeat this is try and do a screen capture off a tablet and do this on a tablet. I just, at the time, I just find paper easier at the moment. So how do you think we go from meters per second to meters per second per second? And I think the common sense solution is that we divide by seconds. So that gives us a definition of acceleration. Acceleration can also be referred to as let's introduce the notation. Let's do it this way. It's delta V over delta T. That is not just a triangle, it's a Greek capital delta, which looks shockingly like a triangle. And that stands for difference in, or small difference in. So, well, I think the delta is difference in, D is small difference. So what we're saying is, and I suppose it makes sense, is that the acceleration of something is changing velocity for a given time period. So let's work out what that means in terms of our graph. Well, change in velocity is going to be v take u. Yeah, because we're going from down there to there. And then change in time? Well, assuming that's 0, which, you know, let's be sensible, that is going to be 0. Change in time is just t minus 0, or let's call it t, because that is what t minus 0 would be. So that's your acceleration. We have a formula. Next up, let's work out what the distance is, how far we've travelled. And I'm going to assume that nobody here knows calculus, understands calculus, or gives two hoots about it. So let's do this the more intuitive way. Displacement is in meters. And we've got velocity as a factor of meters per second. So let's say that meters is going to be, well, that's meters per second. And if we multiply that by seconds, we get to cancel those out, don't we? So that tells us that what we've got to do is find the area under this graph. Now, you could go around and do this with some form of integration and calculus. But look at the shape of the graph. And look at where I've split it. We've got two sections. We've got a rectangle and a triangle. We can work the area of those out. So let's say that the rectangle here, well, that is just multiply the length of that side by the length of that side. So we're looking for u times t. Okay? Now the triangle is that side multiplied by that side, but only half of it. And if you look at this rectangle that we've drawn here, that should be easy enough to see, because this rectangle this line cuts this rectangle in half. So this is a half times V take U times T. Okay, we've got that. So we could say that our displacement, and let me just make sure that this is all on screen, is UT plus that half V take U times T. Interesting. However, what happens if we do a bit of a maths trick of this term? Because this V take U, we can see that in acceleration. We've seen where that comes from. We just want to divide by T. There's nothing stopping us doing that. Divide it by T, but then we must multiply it again by T. And now what you've got there looks suspiciously like what we had there. So why don't we just replace that? Displacement now equals initial velocity times time plus a half. That is now A. That's now our acceleration. And that T times T, well, that's T squared. There's our second equation of motion. We'll come to more of those as we need them, because we can derive them all. I think there are 5 in total, and we can get them all off that graph, if we want to. However, what have we done there? We've worked out how far we're going. We've worked out our acceleration. We can work out speeds. So remember, let's go back to the idea of a 0G hill. A 0G hill is one where your acceleration matches the acceleration due to gravity. So imagine you're throwing a ball. A ball in midair feels 0G because it's moving at the same rate as gravity's pulling it. So the force is not exerting a force on it. The acceleration's not exerting a force. Does everyone kind of get that? Am I making sense, or am I talking a load of nonsense? And by the way, if it does sound like I'm talking a load of nonsense, again, please, please, please do tell me. Because otherwise I will go ahead and carry on. Yes. Yes to what? Yes, I'm making sense, or yes, I'm talking nonsense. Because this is important to get for the rest of it. You don't like formulas, so carry on. In which case, Kaylee, I think it'll start making, or you'll at least see roughly what you want to see. We'll get to the point where we use computers to generate stuff for us. Because if you think I'm doing it all by hand, you nick as well. So, alright, let's kind of work towards our idea. We are going to want to make a 0G hill. Let's think about what happens. Right now, we're going to forget that friction exists. We're also going to assume that you can nick us. Yeah, I'm trying to be polite. I'm trying not to swear too much. I'm trying not to swear at all if I can get away with it. But I'm trying not to swear too much at the very least. So let's... Yeah, you're struggling to see how this can be translated into coaster design. Well, let's get a little bit more theory down, and then we'll do the coaster design part of it. And by the way, I'll prove it in Planet Coaster as well. And I might even try and prove it in No Limit if I can pull it off. If I can learn how to use No Limit quick enough. That could be fun. So you all get to see me make a hash of something at the end of this. So let's remember what happens horizontally. When you throw a ball, let's use the ball throwing example. There's no forces acting on it forwards and backwards. Once it's left your hand, once I've done that, it's got no forces acting on it because I don't care about air resistance and I don't care about friction. They're negligible enough that I do not care. So there's no force acting on it, there's no acceleration acting on it. So it's going to go dead straight until something stops it. But gravity's going to act on it, isn't it? So instead of trying to do this all one by one, all in one, let's try something. I don't have a Games in a Snap command because I am a bad person, Minxie. Yes, I will advertise it. Games in a Snap is tomorrow at 8 PM our time. In fact, let me do a thing. I'll do it as a command. GIS games in a Snap happens every Saturday at 2 PM US Chicago, over on HTTPS on Whack. I should get you to do this for me, Minxie Rose, but I won't. / games in a Snap. For more information, visit gamesinasnap.com. And emoji. Put that one in. Are you happy now, Minxie? So let's say we want to make a 0G hill, which is the same as the ball throwing. We've got to say that the vertical velocity of the ball, well, it's going to start off as u, because u is what we call our starting velocity. So vertical, we're going to start at u. But then, this is for velocity, we're going to have to work it out as, we're going to have to minus GT. What's G? It's about 9.8. And I've written it as meters per second squared because that's the same thing as meters per second, and you'll see it in game as meters per second squared. So free fall, you will be accelerating towards Earth at that speed. Close enough to 10. So after 1 second, you'll be going at 10 meters per second. After 2 seconds, you'll be going at about 20 meters per second, and so on. 20 meters per second, by the way, is about 45 miles an hour. Just to put that in, terms that most of us understand, and someone will probably convert that to kilometers if they want to. I don't know kilometers per hour. And minus GT, it's important that it's minus because it's going down. And then the horizontal speed, well, that's just u. Now, because these are different u's, let's give them subtitles. So let's say that is u sub y, and that is u sub x. So what's the distance covered by each of those? Well, we've got formulas. So let's try the horizontal displacement. So let's call it S sub x. X because it's horizontal. Well, that is really just going to be u sub x times time. speed equals distance over time, multiplied by time on both sides. And you get displacement is velocity times time. Vertically, so let's look at SY. Well, we've got we've got the acceleration, because we're just going to use G for that, and we've got T. Hang on, we had a formula for that, didn't we? We said it's UY times time plus a half AT squared is what we worked out. Well, A is minus G, so we can just put that as a minus. That's a half G T squared. Next problem is, though, we've got to work out what is our X and our Y. Our starting velocity X and starting velocity Y. And this is where this difference between speed and velocity comes in. Velocity is speed and a direction. So me going 20 mile an hour that way and 20 mile an hour that way, same speed, opposite velocities. So we're talking vector quantities, we're talking a quantity and a magnitude and a direction. So if I were to, I'm going to just fire up a sandbox quick. Yeah, whatever, let's just stuff it in the city, don't care. We know that we're going to enter a hill. I'm going to swap us across from the from here. Are you going to play nicely? Are you going to play nicely? Yes, thank you. So let's have a little look in Planet Coaster as a simple build. We'll try No Limits 2 later, or I might try it in a later stream. What I might do is have a break and then we'll do a Learning No Limits stream. Grab a coaster. Because I'm working with kind of ideals, I'm going to say that I want something that's going to have a really short train, or that can have a really short train if I want it. And I want something that I can launch. So let's say Typhoon. Really short train, chain, easy to launch. Let's learn to rotate properly. Let's say it's going to go that way. And let's say I'm not going to do that. Can I launch one of these? Yes, I can. Cool. We're going to launch at... I'm only going to go for about 45 mile an hour-ish. And you'll see that here it says acceleration rate in meters per second squared. Talk a bit, we're not entering orbit. We are learning about maths of roller coasters. But welcome on in. By the way, if anyone does enjoy programming, Andrew looking at you for this, and wants to learn how to program in Rust, or wants to learn how to florp in Rust, as Togglebit lives in Florpsylvania apparently. Hope I didn't dox you too much there. But yeah, we'll launch at about 45 miles an hour. Let's make sure that we get up there. And you know what? I really aren't going to... In fact, let's do it this way. Let's even make you launch up at 45 mile an hour. So at this point, we're what, 6 meters above ground. We are going at 45 miles an hour at 45 degrees. And if we start the test, obviously it's going to crash, but hey, we've got to have some fun. Let's watch it get up there. So we can see laterals are 0, verticals are 1, and forwards we've got some because we've been accelerating. And then it goes and it does that. And in fact, we'll let it do that again. Because what we see when we're flying around, by the way, thank you for the what's it for this. We see that takes an arc. Well, that's a 0G hill. Okay, there's no track there, but that's a 0G hill. We just need to build the track that would do that. Let's pause that because, you know, watching that over and over again is not great. But we see that we're going 45 miles an hour in that direction. And that's the important part of this. However, if we sort of flip back to the notebook, I've got an X component and a Y component. I don't have. Like, I don't have any formulas for 45 miles an hour at 45 degrees. 45 miles an hour, as I say, is about 20 metres per second. You can either try and work that out by remembering everything, or you can do the sensible thing, go on Google and ask it what 45 miles an hour is in metres per second, and it'll tell you. You can convert in game. You've got a pretty good chance of getting that easily. Let's not worry too much about that. But there's a problem. And let's draw this out, because diagrams are quite often helpful. So that is a vector that represents, let's say, 20 metres per second. We want to know what the X component is of that and what the Y component of that is. And we've got an angle there of 45 degrees. And I'm going to do all of this in degrees, because that's what the game works in. So what do we actually have? Well, let's say that 20 metres per second, let's work it out for that, and then we'll do the numbers. So what's UY? Well, let's remember old trig. Let's go back to school. Let's remember, I don't know if anyone else was taught it this way, so Ka Toa. The sine of an angle is the opposite divided by the hypotenuse. The cosine of an angle is the adjacent divided by the hypotenuse. And the tangent is the opposite divided by the adjacent. Well, the tangent we're not going to worry about. That's going to be silly. But we do know that we want to find out this. Now, this side doesn't touch the angle. It's opposite. By the way, to be correct, let's draw the... say that we know that to be 90 degrees. So that's the opposite side. And we've got the hypotenuse. So we can say that sine of 45 degrees is UY over 20. Okay, that's great, but we want UY on its own. So we want to multiply this side of the equation by 20 metres per second. What you do to one side, you have to do to the other. So let's say that 20 lots of sine 45 degrees equals UY. Which is, I can't remember exactly what it is, so what we do is we get our calculators out. Hi there, Holy Seraphimon, how are you doing? Welcome on in. Dis taught this, apparently. I would expect Dis to have taught English more than likely. 20 lots of sine of 45 degrees. Let's just grab a random calculator. That one will do if it's got power. That one doesn't have power. I don't know why I left that one open like that. That's annoying. I might have to use this one if it's got power. Yeah, can't. Has this got power? Nope. We might be using phones for this. Let me plug one of these in, get it charged up. Unfortunately, it's going to have to be the one I like less out of the two of them, but sure. Where's the cables for everything? I lost all my cables. That'd actually be the better one of the two. Give me a moment, folks. Please wait. No, I use my phone. Yeah. Probably should, but you know what? No, I've got actual calculators. I could even just do it on the Googles or whatever, but let's plug this in and see if I can Get something out of it. Come on, plug in. Oh, it's a USB cable. You have to rotate it 3 times. Standard rules. Tell me that is a normal port. And tell me that that will boot up quickly. It has done. Okay. It's fine. So we've got a calculator. Unfortunately, you guys are going to struggle to see the screen on this. That's a shame. Do you know what? Let's stuff it. I'll leave it plugged in. We're not doing it this way. What we're going to do is we're going to go to good old Windows calculator. And I'm not going to be able to show it on stream. Go on, let's do it this way. Let's go. Minxie might have won this one. Calculator. So what are we saying? We want 20 lots of... What? Go away, stupid thing. Come on. So I just really don't want this thing to dox me. Fend. Fend? Sorry, you missed the context of this. You just shout out fend. Okay, so let's say 20 times sine of... We're in degrees mode. This is the thing. Remember to be in degrees mode once you're doing this. So 20 times sine of 45. 14.14. I will take that. Fend is a really cool converter tool and calculator in the terminal. Yeah, but... Meh. So let's say that's 14.14. Then we want to work out UX. I say we can do a similar argument. UX over 20 is the cosine of 45 degrees. So 20 times the cosine of 45 degrees is UX. Funnily enough, I know the answer to that. 14.14 meters per second. You can kind of do that just by looking and going, well, that's a square, clearly. You know, you finish that off, you get a square. Or you could plug it in, realise that cosine of 45 degrees is 0.707, multiplied by 20 to give you the 14.14. Okay, well, we've now got all the numbers we need, haven't we? Except we're using time. Let's assume that we're starting at 0, 0, and let's plug some of this in. So let me go to... Let's see how to do this well. This is going to be the question, isn't it? Go there. Let's go there. Desmos. We're going to go and use a tool called Desmos. And if I go back to there, and we're actually going to do display capture to give us that, we'll go to their graphing calculator. This is a website. I'll stick this one in chat for us. It's that, and there's some green screen jank going on, is there? Okay, let's get rid of that. So we came up with two equations. We said that we wanted UX, which we worked out to be 14.14 times T. Okay, and in fact, let's zoom that in. Give you a chance at seeing this. So that's one equation. X is that, and then Y, we said, for how far up and down we go, is UY times T, so 14.14 T again, minus a half times G, well, G is 9.8, give or take, times T squared. Let's then zoom out on this graph. No, why am I doing that? Why am I forgetting that you have to do it that way? And this is because we're doing t between 0 and 1. Now let's say we're going to do t between 0 and 5. Because that'll get us all the way. And we've got a shape that looks very similar to, if we flip back to the game capture. So remember this shape. Now let's give this another go. Let's unpause that. And let's get that as level as we can. So it is going to be a bit distorted. Doesn't that shape look a little bit familiar? So what we've just done is graphed the track that we need to make. Now we've got 6 meters high already. So we've got to add 6 onto whatever we get. But let's pause this. Yeet! Oh yeah, I never said that this was going to be, you know, without crashing. This is like Kerbal style maths. So let's jump back to there. So, in general, what we need to do is get the track just over 10 meters high. And thank you very much, Miss Fun, for that raid. Welcome on in, raiders. Feel free to join in. We are doing some maths with Planet Coaster. So, it's more educational. And at the moment, we're designing 0G hills. So what we've worked out that we've got to go up by about just over 10 meters. And we've got to do it 20 meters later. Okay, we can do that. I'm going to do this really rough, so it's not going to follow exactly the same profile. But if I were to say, oh no, hang on, let's remember how to Planet Coaster. So let's start building off here. Let's say I'm going to do standard track. I'm going to go about 20 meters, and I want to get that to about 16 meters. Let's kind of guess at this. Let's say that we're going to go to about there. I wish we could see how high that was. And then we'll do that down. That's 14 meters, so we didn't get that quite high enough. Okay, so let's shorten that up. Oh, there. Control Z. Let's try this again, shall we? We're going to go the whole 20 meters. We're going to go to about that angle. Let's build that. Say that comes close, so we'll pull that right back. We'll try and drop that down a bit. Build it. And then we'll go the full 20 again. Or as near as. And you see, I'm not going for exact here. And we'll build that. And we'll just build whatever after. Just to give us another yeet. By the way, what were you playing today, Miss Fawn? Oh, enjoy your lurk. Before you go, do let us know what you're going to find to eat. Gotta let us know. And enjoy your lurk. Thank you very much for the raid. Educational flea! No, we're making roller coaster trains go yeet. It's fine. So I think we've got something that we could test here, haven't we? If I actually remember to build that. And that's going to be somewhat close. And let's unpause. And we'll have a ride as well. Why not? So we'll get on. Watch that vertical G-force meter. So it's going to go, stay at 1, and then it's going to go to 0-ish. And that is very close to a 0G hill. So what we've done is we've just used maths to work out roughly what a 0G hill looks like. And why it looks like that. And we'll pause. And obviously we could have gone one further. We could have graphed it all out. We could have we could work out exactly everything that we needed, couldn't we? And I think we'll probably do that. But that just kind of proves that you can get pretty close. So let's kind of, well, I'm going to go back there, and then I'm going to go back to the notebook. They Are Billions, Miss Fun. Excellent. It's a game I haven't played, but I've seen one or two people's play it. How you doing? You got eaten by zombies. That sounds like They Are Billions to me. Is it possible to get a true Zero G hill? Yes and no. The reason I say that is you could get a point on a roller coaster car to hit Zero G. So you could get, let's say, one person at most to experience the full Zero G. Or one row of people. But if you've got 2 rows of people, because of where the speed is centered in the coaster train, every row has a slightly different experience. So true Zero G is going to struggle. If you've got 16 rows, it's going to be rougher. You know, people at the front and the back are going to get very different experiences. So, you know, if you've been on sort of longer train roller coasters, you'll know that if you sit on the front, once you're at the top of a chain lift, it'll hang you over a drop before letting you go, because it's waiting for the middle of the train to go over. Whereas if you're on the back, it'll start accelerating and really pull you quite fast up the top bit. So that's why I'm doing this with all short trains. Just to, again, take that out of it, because otherwise you'd work out everything for the middle train, then you transpose all the speeds to the front train, transpose them all to the back, and it's a lot of extra messing about that really Planet Coaster can do for you. But we've now got some formulas. We can now make formulas up from this, can't we? So, well, we worked out that UX is now going to be, let's introduce one other bit of notation. Let's introduce the Greek letter theta, because apparently angles are measured as, are labelled theta and after Greek letters. So, well, let's continue the tradition. So that is now that initial speed times the SX is, cosine. And SY, well, that is going to be, if we remember again, U times the sine of theta. Yeah? So, we've got 2 equations. And we can enter them into Desmos as 2 equations. Or we can try and work out one single equation in terms of the 2 distances, because time is less important here. So we can try and eliminate that. Let's give that a go, shall we? So let me just scribe a few bits onto this page so that I remember where we are. So let's say that the displacement in x is our initial speed, our initial velocity, the magnitude of. So yeah, and our initial speed times cosine of the angle. SY will be U times the sine of the angle, theta, and then minus a half. Oh, both of those are times time, obviously. Yeah, I always fluff that bit. Times minus a half g t squared. So some reasonably simple algebra, but we'll walk through it. I want y in terms of x. Because then I can just plot the whole thing. And I can do other things. So let's say that, let's rearrange this one, because this is the easier one. To get time on its own. So we'll divide by u cos theta. Sx over u cos theta. That'll give us our time. Okay, well, that can get plugged into there and into there. And this is where I have to be really careful and make sure I remember how to do this properly. So S of y is u sine theta. Well, let's write it out in full. U sine theta. Let's see if I can learn to write. That would be a good start. Multiplied by the displacement in x divided by u cosine of theta minus a half times g times, again, that whole thing all squared. All I've done is said, well, if t is equal to that, then I can just put that in wherever t is. And now we can do a little bit of messing around. Let's try and mess this bit around first and see what we can get here. So it's u sine theta. Let's do it this way. Over u cosine theta times t. All means the same thing. Oh, hang on. And there's an sx in there somewhere. Not times t, sorry. Times sx. S sub x. That makes more sense. Minus, well, we can do a similar trick here. We can go, you know. Actually, we can't yet. We'll do something else here. We'll say that that's a half times g. Now, to do that whole fraction squared, you just do the top squared divided by the bottom squared. Because to multiply fractions, you multiply the numerators and multiply the denominators. So that's s sub x times s sub x over u cos theta times u cos theta. So I can rewrite that as s of x squared over u cos theta all squared. First thing we notice, we've got u times something over u times something. So the u's cancel. Second thing we notice, we've got a sine and a cosine divided by each other. So let's look at this triangle again. Let's kind of think about something here. I'm going to draw it deliberately like that. H, O, and an A. So sine of theta, we said was O over A. O, no, hang on. A over, O over H, yeah. Here we go. Opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Well, what's sine of theta over cosine of theta then? I could make the argument that it is sine of theta times 1 over cosine of theta, which means we can just flip the cosine upside down, can't we? Yeah, you see, Andrew's kind of spoilt this already, but sure, you're kind of giving a hint away there. So it's O over H, opposite over hypotenuse, multiplied by, well, hypotenuse over adjacent. And the rules for multiplying fractions is you multiply the numerators and the denominators, so I'll just extend the bar and say it's those two multiplied together. H's cancel, which is opposite over adjacent, which is the tangent. That's tan of theta. So if we're simplifying this part, we can go from something that looks really, really messy to becoming, I'm going to move the S sub x to the front because multiplication doesn't matter the order. So it's S sub x times the tangent of theta minus a half G S sub x squared over U cos theta all squared. Okay. So that looks narky, doesn't it? And I would say that that is pretty narky. But it means that what we can do, if we go back to our graphs here, let's turn that one off. And let's say we're doing it now without a t. So what have we got? S sub y. So y for this is x times the tangent of theta. Well, x tan of, what did we say? Let me make sure that this is in degrees mode before I do anything else. Menu, no, not menu. Remember what it is. It's in there. Okay. Graph settings. Degrees. Click that. Sine of x squared over 2 lots of x squared minus pi halves divided by pi. We're not just putting random graphs in. I'm not playing that game at the moment. And I don't know that one. It's not a random graph. What is it? I get the feeling you're trying to jump a long way ahead and ahead of where we need to get, where I want to go. Remembering that I'm not pitching this at people who are like your level maths. I'm pitching at intelligent people rather than like stupid brainy people. Or stupid mathy people, let's say. Because let's face it, people here are all stupid brain. So, x times the tangent of, well, we're going to go 45 degrees. Minus, remember I said a half there. G, we say is 9.8. Your degree is computer games programming, there's lots of maths. Yes, there is. My degree is computer science. There's also maths in there. We have people here who've got degrees in English, in many other subjects where they've got huge qualifications or whatever, and there wasn't much maths. So let's not let's not go too far. You make websites, some of your seminars had crayons. Yeah, according to Bo, I think some of ours actually did in computer science. But that's a different story. How are you doing? Were they tasty? Oh god, here we go. I'm just going to finish putting this in. What did we say? U, which is that foot. Hang on, why am I putting foot? Oh yeah, I need the U in here. I need the 20 meters per second there. That's where I need it. Okay. Cosine of, do we say 45 again? All squared. And, oh look, we have the very, very same graph. We've just done it in one equation. Okay, now we don't have to worry about t being a certain size. We've got one equation. What we could do as well, because Desmos is kind of clever on this, is instead of subbing in what we said, I could say that A is going to be an angle. So A is the angle that we're going to go for. And here, let's use U. And put sliders in. So that's the formula that we came up with. If we look in the notebook, it looks slightly different. But you know, we've got y is x times tangent of A for the angle, minus a half times g, which is 9.8 on Earth, SOX squared over u cosine angle squared. So yeah, it's the same formula. Would people be happy with that? And of course, given that, if I sort of put in some sizes like the angle's got to be somewhere between 0 to 90 degrees, and the speed we're going to say is between nothing and, say, 30 metres per second, why not? What you'll notice is we'll have an angle, yeah, speed can't be 0, I agree with that, and it will be horrible, but sure. Well, let's have it at around that 20 mark again. Let's have the angle back up to 45 degrees. And what we've got now... Oh yeah, no, I agree with that, Jed Levi, but again, people aren't going to do that. Let's not try and do that. And yeah, it goes to... And in fact, if we do it on the graph, because tangent of 0 is undefined, it just tells us to go away. So we're not going to have that problem. Desmos is quite good. It's like if the angle is 0, you'll see that. If the angle is precisely 90, it'll again tell us to go away. So I think that's kind of reasonable. Well, we've now got essentially a 0G hill generator. You say that we're going to start at whatever angle you want. Let's say we're going to start at 60 degrees this time. And that we're going to go at 20 metres per second. Well, that's the shape that you would need to trace. You want to go faster. And of course, that hill's going to get taller. Which kind of intuitively makes sense, I think, you know. If you're going slower, it'll go smaller. And, you know, if you want a flatter hill, it'll go a bit longer, and then it'll come and shorten down. You want your coaster to have a lateral 5G. We're going to talk about banking soon, and if you're going to put 5 lats on a coaster, I ain't riding it. Tell you that for nothing. So I think intuitively we've got something here that makes some semblance of sense. But what did I do? I wanted to know what this height was. Also kind of handy would be how far away this is. The height, we've got a reasonably simple way to work out if you're happy to take a dive into a little bit of calculus. And this could become awkward, so let's first of all try something here. Let's get this x squared term kind of on its own. So this is only going to be a small rewrite. I'm not even going to calculate that point yet. I'm going to calculate this one for fun. I mean, of course, we can just read it off the graph. So if this goes over anyone's head, the answer is go to Desmos, put the formulas in that are of interest, and I'll put a quick blog post up at some point somewhere with these in. I'll link everyone to them. But I don't see why I can't do this. Why I can't go u cos A squared here and then not even bother putting it there. And again, that graph looks exactly the same. I've just done a little bit of a mathematical sort of rearrangement. What we have there is a quadratic. Now, how mathy... Do people want to see me try and derive the quadratic formula once we get to that point? I can do it, and I do know a sneaky trick on how to do it, so I might show it off just for fun. But this point is very interesting, this top point. How do we work this one out? The 9.8 over 2, yeah, it could as well. You are correct, you could do that, and just... And that, again, is exactly the same. And I think you're hinting at what we're going to do now anyway. What's interesting about this point? Or just 4.9 over 1. Yeah, we could, but I'm not going to. I'm actually not going to do that. And the reason is that I want that to remain G, ideally. I've just put a numerical approximation in. I mean, what that really would be something more like, and G equals 9.81, whatever. That's close. So we might as well just leave it like that. But again, what do we notice about this point? What do we intuitively know? We know that it's the highest point on this graph. But what does that tell us? That tells us... Nice versatile equation so we can build coasters on Mars. Absolutely. Yeah, of course we can. Why not? But we know that that's the highest point on this graph. So we know that if we look at the slope of the graph, it is sloping upwards. Okay, it's sloping upwards less. But all the way until we hit this point, we're going up. We're climbing. And then everywhere after this point, we're going down. So we're going up, 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 all the way. Getting to there, and then down, 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 down. At this point, and at this point only, we are flat. And we are absolutely flat. So 10.204. So let's say that we just put y equals 10.204, did we say? And that will pretty much intersect once. Is it safe to assume that the parabola is symmetrical? Yes. Just on the grounds that it is a parabola, it's symmetrical. We know that. Again, I'm not taking friction into account because that does make it a bit tougher. So in Planet Coaster, you probably do the back half ever so slightly steeper than the front half, whatever. So we could identify the 2 points where y is 0, take the midpoint and solve for y like that. We could. In fact, what I'm going to do is I'm going to take a quick break in a minute, and we're going to try it both ways. We're going to try it the way I was originally going to do it, which is more complicated than that. And we'll do it the way that you're thinking. Oh, and by the way, because of how this is constructed, 0, 0 is always one solution. So yeah, very, very good spot there. I'm not even sure I want to explain the other solution now, because that was a stunning spot. Right, I'm going to take a few minutes. I'm going to take a very quick break. I will see everyone in like 5 minutes or so, because I need to make a brew. Because I'm not doing the rest of this without coffee, and all the rest of it. So stand up, have a walk round, stretch your legs, take your eyes away from the computer for a few minutes, please. Let's get that sorted. Let's get ourselves rested up, and let's see if we can do this. Homework for chat, solve for y equals 0. Yeah, okay, if... I mean, 40.816, roughly. Alright. I'm not going to say that chat should do that homework, in fairness. Hey, I've got computer tools. I can do that. Again, from what we're going to do in the next part of this, what we're going to do soon about working out what this value is exactly, working out what that value is exactly. Wolfram Alpha is one answer. Or, hey, we're on Desmos. We've graphed it. We hover our mouse over. We get the answers. Both work. But yeah, I'm interested in checking both of these out. So I will see you all in a couple of minutes. Okay, folks. I'm back. I'm hoping everyone's had themselves a drink, gone and had a answer to Cool Nature, taking a bit of time away from the computer. Thank you muchly, Des. So, when we last left, we had a formula that I'm just going to write down on the next page because it's going to be easier than working on this page. And it's going to show us, it's going to be easier. So I'm going to stop using S sub Y and S sub X. We're just going to use Y and X in this, just to make life easier. So we'll define Y to be the distance up we're going, and X to be the distance across. So Y equals, and I'm going to slightly change orders around just to make life a little bit easier. So tangent of A, I'll keep A as the angle for this. Probably shouldn't, but this is exactly what we put into Wolfram Alpha. Times silly looking X minus G over 2 of U cosine A all squared, lots of X squared. And I made the assertion that if we go, we'll go back and look at the graph again. I made the assertion that everything up to this top, everything to the left of this top point, we're going up. Everything to the right of it, we're going down. So what we've got to do is answer the question, well, what is the gradient of this graph at any point? So given an X value, we don't want to know what the Y value is. We want to know what the slope is of the graph. Because if the slope is 0, we know that that is the X value. Where at the top, we know that that is how far we go to get up to the top of this hill. Does that make sense to folks? Unfortunately, the next part of this, I'm going to ask you to trust me on. Because otherwise, proving this is going to be very, very difficult. And honestly, I don't really think anyone wants to see me go through the proof. I'm happy enough to do it at some point, but I don't think now is the time. So let's work out, given an X value, what the slope is at the Y value. Now, the general gist of this, I will go through the general gist of how this works. So let's go back to our notebook. And I'm going to draw a very, very zoomed in bit of this. Let's draw it like that. I've got an X value and an X value plus a little bit. Call it H. And I'm going to say that as that H goes towards 0, that line becomes straight. So that line there, let's draw that again in sort of red. That line joining those values becomes straight. Because we're getting that H to be smaller and smaller. So we're bringing these two bits closer and closer and closer together. Until they are so infinitesimally small that it is straight. And then we've got a Y value there. and a y plus. Trying to think exactly how how we would notate this. I don't know. Y plus whatever. So what we do is we want to work out the slope. So that'd be dy, the whole thing would, wouldn't it? Be difference in y. That would be difference in x at that x value. So we're looking for, and this is just going to be the line y equals f of x. F being a function. So that is a function, x plus 2 is a function, whatever. And we want dy by dx, we want rise over run. We want the difference in y over the difference in x. So that point there, well, y at this point, let's not call these y, let's call them f of x, which would be that point, and that would be, well, f of x plus h, and dx is essentially h for this. So put x into the function, you get that y value. Put x plus h into that function, you get the you get that value. So the difference between those is the difference in y. Okay, we can do that. We go f of x plus h minus the f of x. And dx, well, that's the h. Problem is, we want h to be as close to 0 as we can get it. So we're looking for a limit. And it's notated like that. So the limit as h goes to 0 of f of x plus h take f of x all over h. That gives us exactly what the rise over run, or the gradient of that graph is. There's a problem though. That h cannot be 0. We need to get the limit as h approaches 0, but as soon as it hits 0, undefined. All bets are off. So you've got to get it damn close, or you've got to do silly trickery. Now, we could go through and plug this in, do all the maths. Or we could cheat. And we could know a couple of rules. One of the rules that we know, and that we get to at A level, is let's carry on using the same notation. Let's say y equals x to the n. So that n is just a constant number. That would imply that dy, rise, over dx, run, is n lots of x to the n minus 1. So you subtract 1 from the power, and you bring the power to the front and then subtract 1. So let's do 2 examples. Let's say if y equals x, well, x is the same as x to the 1. dy by dx in this case, let's just literally follow the formula. 1 lot of x to the power of 0. Does that hold fair? X to the 0, well, that's 1. As long as x isn't 0, that's 1. Actually, no. Yeah. If we're doing 0 to the power of 0, just don't. Let's just say it's 1. Trust me, it's fine. Okay, let's do a second example. Let's go y equals x squared. Well, dy by dx, again, rise over run, we would get 2 lots of x to the 2 minus 1, which is 2x. 2 minus 1 being 1, anything to the power of 1 is itself. Those are the important ones that we need to know. Anything else that we need to know is that any constant multiple of something stays the constant multiple. So if you've got 2 lots of x to the n, then the differential is 2 lots of n to the nx to the n minus 1. So constant multiples, we can just ignore. They're fine. They stay the same. Adding and subtracting differentials, just add and subtract as normal. We don't have to do anything special. So what we want to work out for this, if we've got that, then we're going to say that differential, well, rise over run is tangent of a. Now, a is a constant. We're only doing this with respect to x, not any other number. This is only with respect to x. So a is a constant. U is a constant. So the tangent of a constant is a constant. Always. Constant times the differential of a number, times a number, differentiated, is constant times the differential of that function. So to get this part, well, that's just x to the 0 times 1. That's 1. In fact, we've got the answer there. Anyone wonder why we did these 2 examples? So that'd be the tangent of a minus, and again, we get the same trick here. And I will write this out in full, and we'll work out the thing here. So we'll say, g over 2 lots of, again, u is a constant in this because we're not differentiating with respect to u. We're doing it with respect to x. So u is a constant. Constant multiplied, well, a is also a constant. Cosine of a constant is a constant. Multiplied by a constant is another constant. Squared is a constant. Multiplied by a constant is a constant. A constant divided by a constant, g, remember, is a constant. So all of that is a constant value. That's just a number in this formula. So u cos a all squared there. And again, we remember our rules. X squared, the differential. Oh, look, we've done that one already. So that's 2x. Oh, look. To multiply by 2, we could just put that in there. And 2's can cancel each other out. So what we've got is... Literally, I'll just write it again a little bit neater. Well, yeah, me and neat. That's a laugh. Tangent of that angle minus... Again, the x can go inside, so we can just go g lots of x over u cos a all squared. Ah, well, Ming Zeros is back as well. Excellent. So we've got that. Why don't we graph this? I think we should. What are we up to? We're up to working out where this top point is. So just as a brief reminder, we want to know what that top point is. We've got two ways of doing it. I'm doing it potentially the hard way at first. So we've gone over what differentiating a function is. Now, actually, let's go one further. We've agreed that at the very top of this hill, you're going dead straight forward. You're not going up and you're not going down. All the way before then, you're going up. All the way after then, you're going down. So the slope at that point is precisely 0. So the rise over run, so how much you're going up over how far you're going across, is 0. So we worked out that could be represented as dy by dx, difference in y over difference in x, and we trusted Gareth that there's a rule here that works. So now we've got dy by dx is this. So I'm going to graph that. I'm going to type it in while we're still on this screen, and then we'll flick across to it. So that is tan of A minus gx over. Hold your horses, Jed. I'm going to do this bit first, and then I'll move us back to the screen. Do you know what? We can go to the screen now, can't we? Let's do it that way. And then that's got to be all over u cos A all squared. And lo and behold, Jed Levi gets it dead right. You will notice that point and the point that we see up here. So can I rearrange these around? Yes, I can. So that point there, 20.4080, is directly below that top point. So we've kind of worked out that the gradient is always dropping down, and at some point it crosses 0. So everything above 0 means that we're going up, and the higher above 0 is, the steeper it is. And once we go below 0, we're going down. The further below 0, the steeper it is. So we can solve for that equaling 0. So we set this function to 0, which gives us that an x value. I'm not going to do it necessarily for this one. We could try and do it in the general form. I think it's going to get complicated. And then we get that. Actually, let's do it for this one. Let's follow this through in numbers. Let's follow it through. It's a great way. Yeah, the derivative is literally a measure of the slope. It is rise over run. And you know, if we were to change these u values, that would all figure. You missed an amount of steps, Minxie. What I will say is, this bit you don't actually need to know to do anything in Planet Coaster, because all you do, I mean, I wouldn't do this normally. This is just to show how the maths works. Honestly, I just click on that graph and say, oh, just over 10 metres up, and it solves there. This is just for kind of devilment at this point. And I missed some steps out as well. So, shall we have everyone happy for me to do a quick revision for Minxie, just to kind of solidify this and help her out? If you're not, tough luck, I'm doing it anyway. It's to fulfill the educational portion of the categories. Hey, I've got a graph on screen. We've fulfilled that. That's fine. So what we said was that we wanted the top of that graph. So that's where the slope is 0. That's where there's no sloping. So what we then decided was, well, we've got to work out, and by we I mean I, What was then decided by me was that I had got to work out how to work out where the slope was on this graph. So I wanted, instead of this, which is a function that gives us the height above the ground at any given point on this particular 0G hill, I wanted to work out, well, what is the slope? What is the angle at every point on this 0G hill? And actually that becomes, well, what's the slope? What's the rise over run? And we can get the angles from that. And actually that's not a bad thing to know. Because if you want to build the hills in smaller bits, you can get the angles all right. I'm not sure I can be bothered with that particularly. It's a lot of work, and what I might do is write something. I might do a programming stream where we work the maths out and program it. Wouldn't it be easier using trigonometry for angles? Drakon? We're going to use calculus because we only want a 0. By the way, welcome on in. How you doing? Haven't seen you... Well, no, yeah. I'm hoping everything's well. Let's go that route. Are you still streaming these days? Because I will ask. I haven't seen it for a while, so if you're planning to get back into it, I'm sure Mix Heroes would be more than happy to give you a shout out. Or she'll do it anyway. Yeah, don't feel pressured back into streaming. By the way, no one pressure anyone into it. Even if they get shout outs, no one pressure people, please, yeah? Let's all be awesome. Just streaming soon. By the way, we will take this example to promote Games in a Snap. Games in a Snap, by the way, for tomorrow. Folks, tomorrow at 2 PM US Chicago time is Planet Coaster in a Snap. So, please, please, please be there to watch that. And we will have a play. So the idea is, I want that dy to be 0 with respect to that x. So going back, let's kind of get back to where we were. So that is a function that says what's the height of the coaster at any given point, given that we are doing a 0G hill. I want a function that says what is the gradient, what is the rise over run. Because if the rise over run is 0, that's cool. So we worked out, we came out with the fundamental definition of the differential, which is rise over run is as our number h goes to 0, a limit. So we do the function for both, find the difference, divide it by the limit. So it's very much, that's the rise, and that's the run for any function. And we said that we could plug that function into both of those, do a lot of math, a lot of boring algebra, and work it out. But we could also accept and trust Gareth, which one should never normally do, but on this one I think is reasonable. One should trust Gareth and suggest that we know a rule. We know that if y is x to a power, by the way, that power doesn't have to be an integer. Doesn't have to be a whole number. But it is for now, and we'll keep it there. But the rise over run is equal to bring the power to the front and subtract 1 from the power. And we're kind of going with that as the idea. And we did a couple of examples. So if y is equal to x is x to the power of 1. Anything to the power of 1 is itself. Then dy by dx is 1 times x to the power of 0. Anything to the power of 0, with the exception of 0, don't go there, is 1. So that's 1. We did the same trick with x squared. We said, well, let's bring the power to the front. Let's subtract 1 from the power. Oh, look, 2 take 1 is 1. Anything to the power of 1 we decided was itself. So it's 2x. Then we said that any constant multiplied by x, you can just multiply the differential the same way. So if you want to differentiate tangent of a, which tangent of a constant is a constant, times x, you're just going to get rid of the x. Similar argument here. We're going to differentiate the x squared to give us the 2x, and then just multiply it by this constant in front. Because u and a are constants here that we supply, we're just going to do that. And all that does is cancel out that too. To give us this formula at the bottom. This formula at the bottom, I have plugged in to there. And what we should do is I should ask the question of why are you the same colour? So can I change colours of graphs at all? Because this is rather confusing that they're both the same colour. Can I? Yeah, let's change the gradient one to be that. Ooh, what do lines? Oh, that. Okay. So what we're saying is, at any point on this graph, so let's say at this point, the rise over run is that. The same x value. The rise over run at this magical point is 0. So we can solve this where x, we can make this equal to 0, because what we should put there is y equals, really, or dy dx, but that would then give us something really weird. So we can set that to 0 and solve this equation. 4x, and that'll give us an x value. And I think we're actually going to do it. I think we should. So I'm going to scribble this formula down, and I'm going to solve it for x, in theory. And this is going to get messy. So be ready. Make sure you've got a mug of something. I've got a mug of decaf, because this is going to become rough. So dy dx is tan A minus, I'm going to make this easy for myself, g over that u cos A all squared, lots of x. Took you ages to remember sine over cosine. Finally understanding this though. Yeah, it can become interesting. It can become, just Google it or use Desmos or whatever. And we're going to solve that. We're going to suggest we're going to set that to 0. So if we add this on both sides, so let's say that we're going to say tan A, you can put the brackets in, is equal to g x over u cos A all squared. Cool. Let's multiply that. Why Google tangent is sine over cosine is pretty simple. Yeah, but, you know, it's simple for some people, not for others. This is about sort of gaining an understanding. If you know, it's simple to some people, it's not to others. You know, some things that I think are simple calculus are not. And then someone will come to me with a line of Shakespeare and I won't even be able to read it. It's horses for courses. So I don't think that anything I'm showing here is simple. Actually, let me reiterate that. Nothing that I am showing here is simple. This is not simple. This is absolutely not simple. If anyone is even understanding the gist of what I'm saying here, you're doing incredibly well. Just because I might be making it look simple, trust me, I've practiced a lot of this yesterday. I actually have prepped for this. Not as much as I should have done, but I have. So we've got that. Right, I want to multiply by, let's just do this all in one go. No, Bo, No, it isn't. I mean, thank you for putting the kappa there. But yeah, really, that is not the answer. We know that. I'm going to take an extra leap. I'm going to multiply both sides by that and then divide by that g. Just to get x on its own. And I'm going to swap the sides as well. Because I don't think everyone wants to watch the boring algebra. So x equals, what did I say? I was going to multiply by that. Okay. Tangent of A times u cos A all squared. And I said I was going to divide by g. Sure, can do that. Okay, so that is the solve for x. So if you give me a velocity and an angle, I can tell you how far along you go before you hit the top. That's great, but I want to know how high up you go. So, for the actual function that we've got, we have, and I am again copying this down because I've got the screen in front of me still, we've got y is x tan A minus g over 2. Oh god, this is going to get messy. I can see this already. That all squared. Lots of x squared. Okay, so given that we've got an x, let's plug it in. Oh god. Give me strength. This is going to get rough. Let's plug that x in first. I'm going to skip steps at this point. X tan A, well that tangent A just gets multiplied by that one, so it's... And I'm not using the stupid tan squared notation. That times that minus, I'm doing this on two lines now. So let's I will write this out in full and then I'll do the simplifications. G over, gotta try and remember get this here. Hang on, what happened in the line where x changed to y? Okay, that x, that is x equals, that is, that's the x position of peak. So that's the x position of the peak of the slope. That is the equation of the slope. So I'm saying that that x needs to get shoved into there and there. Does that follow along? And what we're doing now is just this, is that substitution. So rather than solving for x, well, we've solved for x. We've just done it in the general case. Because g is 9.8, a is that angle which we're going to say is 45 degrees, u is 20 meters per second in our one example. But this is the general case solution. Yeah, we're going to do it all in one go. We might as well have a formula that does it. So if I were doing this in a 3D area, I would add a z-axis as well for this, computing the z-axis using the same. A 0G hill doesn't work in 3D. Essentially, you would be looking at surfaces at that point. At which point you've got partial derivatives, at which point I would just refer you to a YouTube channel called Tom Rocks Maths, Dr. Tom Crawford of Oxford University has done the most approachable intro to that I've seen. But essentially, you're looking for critical points on a surface. That is way more complicated. You add a third dimension in and try and do the maths on that, and you'll understand why games were 2D for so long and why the jump to 3D was so computationally intensive. It's... I mean, Andrew will probably be able to... Wow! My mug is actually blue, not green. Just putting that out there, this is not a green mug, this is blue. I did say my green screen was going to be janked up tonight. So let me continue with this substitution. Which is looking like... And then x squared, well, what's the x? Yeah, it's going to be... You can just... let me remember. Can you do... Yeah, you can. You can do what I'm doing here. I'm essentially not quite doing the substitution as simply as it could be. Because I'm squaring that at this point, which means I can square that, I can square that, and square that. Please feel free to ask whenever. That's to the power of 4 because it's squared and squared again. Yeah, ask away, Jed Levi. Hi, Trilled. No, 0G Hills. That's all it is. Is it possible to simplify the numerator for x? Two lots of something squared. Hang on, no, sorry, x. To simplify the numerator. It probably is. My trig identities aren't that good. I am sure there's a trig identity there that I could use. In fact, there is one. But, oh, damn. Should have gone for it. Actually, no. I could have gone for it, and I could have got one. 2 sine x cosine x is sine of 2x. Could have gone for that one. There's another one I could have gone for, which I could have just squared out that cosine a on its own in its own right, done tangent as sine over cosine and cancelled one of the cosines out, and I could have gone sine a cosine a, yeah, and then done your 2 sine x cos x. Honestly, I don't know if that's the right answer. I wonder if this is a better form to have this in. And I think that the reason for that is I think I'm going to get more cancellations down here. So, the top line is pretty simplified. The bottom line, we've got a g and a g squared. Well, that squared can cancel with that g. The u cos a to the 4 can now go to u cos a squared and cancel all of that lot out. So, the whole thing is looking more like y equals tan a all squared u cos a squared over g. And then what we're doing, we're subtracting tan a squared u cos a squared over 2. So that's not too bad, because as soon as you work out that numerator, it's the same as that numerator. 2g, you are right. Well spotted. That actually, yeah, I only cancelled the exponent. That's good. Well, that's handy. That makes life really easy because I can do something a bit silly here. Why don't I just multiply by 2, top and bottom there? Because that changes nothing, does it? Would everyone agree that that changes nothing? Just multiplying by 2, top and bottom. So a half is the same as 2 quarters, is the same as 4/8, is the same as 8/16. Which means we've got a huge simplification. 2 lots of those take away 1 lot of those is 1 lot of those. And because we've got the same denominator, we can do that. So actually, it's just that half. So y is actually, for this, all of this. It's just this half of it. All over that 2g. Shall we plug some numbers in and see if I've got this right? I think we need to plug numbers into this. And the way I'm going to do it, do we simplify the numerator now? Could we be bothered? I'm not sure I'm that bothered about simplifying the numerator. I mean, we could do that, but at this point, who's going to calculate this by hand? And yeah, it simplifies a bit. Does everyone else want to see the numerator simplification and see if I mess it up? Okay, I've just sold it to everyone by see if I mess it up, haven't I? Sorry, let's do it. Let's prove. Let's mess it up. Which is the I'm trying to remember. Okay, we're using that identity. If we're using that identity, I am not proving that identity. I mean, we don't have to do. Let's just go. Even if you've worked this much out, what you're actually going to do is probably go to there. I'm not even going to verify graphically. Yeah, do you want to verify graphically? So, I mean, there is a way to do that because we'll just say y equals tan a squared if tangent squared is sine squared over cosine squared, would the cosine squareds cancel? No, because there's a u. Oh, there's a u squared as well. You could do it that way. I think you're right. I think you are. Well, let's try it. Yeah, I'm going to do it the normal way first, and then what I'm going to do is add another one in with the cancellations in that I think you're right on. Remember, I only have an A level in maths. I don't have, degree level or whatever. The album. Which album? The U2. Oh, U2. So what's it? I've got a G in here as well now. So I can do that. So what we've just verified is that Y value just touches the top of that. So our maths is right. Now, let's say that Jared Levi is correct on something. We're going to assume that tan A squared is sine squared over cosine squared. I'm going to suggest that that's probably true. So if I say that it's going to be sine of A squared. Yeah. This is the maths behind some of it. It's not always something you need to know. But I think this simplifies all to be this. Which actually at this point, that U can just get chucked in there, can't it? And that just all goes over 2g. I think you're right. I think, Jedi we have a very simple very much simplified formula. I like that one. I think we run with that. I can't think of a more of a simplification than that. And again, if we look at how all the lines change, given the angle changes or given the speed changes, that all seems to hold true. Everything that we've stated with these sliders involved does seem to hold true. What I'm going to do is I'm going to save these graphs for everyone. So, I mean, we don't need to save that one. Let's get rid of that earlier one. But all of these we're going to keep. So we've now worked out that given... And we might as well do the X version of it as well. Let's stick the X one in here. Just to prove a point. Which was, let me just remember how to type. So this was the one that we worked out from doing the differentiation. Hi there, Grog the Wonderful. Welcome on in. Oh, I'm clipping here. I'm going to turn my mic down a little bit. Need to start thinking about putting compressors on this and all that nonsense. So it's this. I'm not going to do any simplifications yet. X equals that. What are you moaning about? Use the parentheses around that. Okay. Yeah, you want that to be bracketed. So, you know, again, given different angles, these all work. So we've got most of this puzzle. By the way, can we use a similar argument here of cancelling things out? So tan is sine over cosine. We could. Because we could go something like x equals... Let's pull the u squared out to the front. Then we've got a sine of 2a over 2... let's not go... Yeah, over 2g. Because 2 sine cosine of x, so we've got to halve it. That's the same formula, I think. Actually, look at that symmetry between the two of those. What we are doing, yeah, I think we've got it. And I think, you know, again, let's just sort of play about with these. And isn't... I've only just noticed, because I've only seen the fully simplified forms of these. But look at sort of the purple equation and this red one. I just really love the similarity between them. You know, they're both over 2 gravities. They've both got a sine. They're both sine of something. They're both multiplied by u or u squared. I mean, to sort of make it even more... What's it? You could do that to bring out the symmetries. That's the same thing. So it's sine a squared or sine of 2a. And that is the only difference. Have I literally just done what you were expecting, what you were hoping to see? To distribute the squared. I never expected to see, you know, something that nice come out of that. And all of this is all about the humble parabola. And we ain't even solved it yet. I mean, we've got We've worked out where the top is. What we haven't done is worked out where this end is. We've got more fun to go for that, haven't we? Would people like to know how to work out where that end is? Oh, sorry, Grog. What's going on? What are we calculating? Let me do it this way. I wanted to make a 0G hill in Planet Coaster. This is where this all comes from. So I've set this up to go 45 miles an hour, which is, all bar the shouting, 20 metres per second on a 45-degree angle. And I wanted to mathematically plot roughly a 0G hill. Now if we look at the vertical G-force, it goes down to about 0-ish. Sort of from there to there, it's at about 0-ish. So if I try and toggle the pauses at the right time, so there, if you notice, the G-force is dropping, and it's near enough at 0 to there, the vertical G-force. So people feel very, very floaty, and that's an exciting feeling. And if we carry on playing, it's still hovering around that 0 mark until there. And then it goes up because I wanted to just yeet the cart, because why not? But it's calculating what this looks like and how to make this, you know. I could probably add some smoothing of the height in there. Oh gosh, hang on. That was bad. That was exactly not what I wanted to see. But you've got that as an option. Okay, let it eat itself further. And what I wanted to do was show people that you can actually work out what those heights should be, what those distances should be. You can work out the whole profile of that hill. You could go, I want a 0G hill. Let's work out how to force it to be 0Gs. And from that, you get quite a lot of very, very interesting maths. So we've worked out the equation of that hill. And, you know, I've parameterised this in Desmos, so I've got angle of entry on a slider. I've got the speed in as a slider. We might have to do another stream of this. I did not expect this to run on this long. I didn't expect to be having... What are we? We're over 2 hours in. And we still haven't finished on the 0G hills yet, and the interesting maths behind it. But we've got a slider for entry speed in meters per second, a slider for the angle that we enter this hill at in degrees, and we've worked out from all of this, and we've got a slider for gravity, but I've just set that at 9.8 because that's about right. It's good enough. It's good enough for government work. So, we've worked out that we've got equation 1 there is the path that the train follows. Number 2 here is this line. This describes the gradient. So this describes the slope of the train, or the rise over run. So it's, this is where it's going quite steeply up, down to perfectly flat, down to quite steeply down. We've worked out, we've got a couple of equations here that describe, the value of where this top point is. We've got that first one, and then we simplified it, so let's take out the unsimplified versions. We've got some rather elegant looking equations for, given a speed and an angle, and knowing what gravity is, how high is this 0G hill, and how far along is that midpoint. Now, another question, and none of this is friction. If we put friction in this maths goes really, really, really crazy. I want to know now, where this point is. Now, Jed Levi, I believe it was, came up with an excellent observation, only we're going to try and abuse it backwards for now. And it's just double of this. So if we stick in fact, if I copy that whole equation and take that 2 from there, that's one way of solving that. And now we know exactly where that is. But that's a lot of work to go through all of the calculus and do that. So let's solve this a different way. And what we've got is a quadratic. So let's look at solving quadratics. And I'm going to write this equation back down, and I'm going to write it in a slightly different form. I'm going to set it to 0, because I want the 0 value there. I want y to be 0. So let's go back to pad and paper. Pad and pen. So what we're saying is minus... Oh, I'm doing this all based on A-level maths. So if you know A-level maths, you've got most of this. So I'm going to say minus g over all this nonsense. 2 lots of u cosine A squared x squared. You knew A-level maths. Oh, you're going to have fun with this then. Plus tan A of x plus 0 equals 0. That 0 is there to show something else. So this is the original parabola. And I've rearranged it so there's an x squared term at the front, then an x term, then a constant term equal to 0. So it is now in the form of ax squared, where this lot is all a, plus bx, where that lot is b, plus, it was my A-level physics project, c equals 0. And again, that 0 is your c. So the question is, how do we solve these? How do we solve equations in this form? You could try and factor it, but honestly, trying to factor that lot, that's going to be a pain. You could try and complete the square. That's going to be a bit of a pain. So there's the quadratic formula. I can remember it, but do you know what? I'm not going to bother. I'm going to derive it, because, again, I kind of can. I'm going to do something a bit silly, though. Let's take this equation. Yep, again, Jed Levi's got it right, but let's prove it. How would you, actually, Jed Levi, what would you do first? What would you do first to that, to derive your quadratic equation? What would be your first move here? Let's see if you do it the same way I do it. Because that gives me a second to have a sup while you think on what your first move would be here. Bo's first move would be to cry. We're not playing Dark Souls, it's fine. Dark Souls is a different stream, that's when we cry. By the way, folks, if I do stream Dark Souls, I'm going to be in trouble because I'm going to have to... I've got, I'm at ONS now. So you're going to see me hit me head against a brick wall trying to beat Pikachu and Snorlax. X plus m times x plus n equals 0, find m and n. How? Because at that point you've just solved it anyway, because, yeah, minus m and minus n are your solutions. Factoring this in that form is going to be very difficult. And plus, there's got to be something before one of the x's. Or both of them. This ain't just x squared plus bx plus c. I've got that a term there. So that makes your trick really hard to try and do. So what would you do to try and get to the quadratic formula? I'll say that I was hoping that you said that you'd divide through by a. I don't divide by a. I kind of do something weird. I multiply everything, both sides. Yeah, let's do it this way. I'll multiply the whole thing by 4a. Trust me, this might look weird. But it comes out cleaner. And that 0 there, 4a times 0 is still 0. So what does that actually give us? That gives us 4a squared x squared plus 4abx plus 4ac equals 0. Okay, let's subtract the 4ac from both sides. So we've now got 4a squared x squared plus 4ab x equals minus 4ac. Well, 4 is 2 squared. Most people know that 2 squared's 4. I know that 4 is 2 squared. So we can do 2 squared times a squared times x squared. Well, that is 2a all squared, isn't it? Because 2 times 2 times a, there's your a squared and there's your 4. Plus 4abx equals minus 4ac. I've left a gap there on purpose, because that looks awfully close to a perfect square to me. Let's see if there's something we can do to turn that into a perfect square. So for something to be a perfect square, I'm going to go my usual route. Well, it's 2ax and 2ax, because 2ax all squared. Yeah? So we know that we've got to have a 2ax here and a 2ax there to give us 2a squared x squared. We've just got to work out what goes there and goes there. And we've got a 4abx, so we need to put we need to split that in half, because we've got to add up all 4 values that go in here. That's exactly what I'm doing. So it's 2abx goes here, and 2abx goes there. Well, 2ax times what gives you 2abx? 2ax times b, I would say. And then that missing value, because what we've done, we've accounted for that term there. We've split that term in 2 and accounted for it there. And we've just found ourselves a mythical third term. Wouldn't it be lovely if this equation were 2ax squared x squared plus 4abx plus b squared? I think it'd be really lovely if that were the case. So if I add a b squared there and add a b squared there, I'm doing nothing wrong. I can add the same number to both sides of an equation. And what we've just done is we've factored that into the following. We've now got 2ax plus b all squared is b squared, take 4ac. Now, ain't that starting to look familiar? If I cancel that square out, and I say it's got to be plus or minus the square root, because minus 1 squared is 1, 1 squared is 1, minus 2 squared is 2, 2 squared is 2, so plus minus square root is important there. And we've just got 2ax plus b is all of that. Well, let's subtract a b. So let's say minus b, add or subtract the square root of b squared take 4ac. Okay, well that 2a, I'm going to divide by 2a as well. That cancels, and you get the quadratic formula. Ain't that lovely? The usual way to prove this, that you'll see a lot of people do, is you'll see them, instead of multiplying by 4a there, they'll go x squared plus b over a x plus c over a is 0. And go through this process and have a bit nastier algebra. That multiply by 4a really does make it simpler. So that's a bit of a naughty cheat, as in if you know the quadratic formula, you can see that multiplication happen. It's a good one to go for, but it can be done without. We've now got a formula. We've got a quadratic formula, haven't we? Well, let's have some fun with that. And this is where I've got to try and remember it. So, we've got an a value. Right, this is going to get confusing. I'm going to go back to using theta for the angle. So the angle is theta. Just because otherwise we've got a meaning two things. So the angle that we've been calling a for a while, we called it theta, then we called it a. We're going to call it theta again. So a is minus g divided by 2 lots of u cos theta all squared. And that's what we said at the top of exactly that, the top of this previous page. B will be tan A. Okay. I really wish I was Michael tan alpha. Tan theta. Tan theta. Remembering that we're renaming these things back. I wish I was Michael Pennant sometimes and knew when a good place to stop was. Apparently we haven't hit a good place to stop. And C, thank heavens for some small mercies, is 0. That's going to help a lot. That is really going to help us. And what we're going to say is x equals minus b plus or minus the square root of, I've written this down too many times, all over that. The reason that the c equaling 0 helps us out is that whole term 4ac is 0. So I'm not even going to bother substituting into that. So x now has to equal minus tan of theta plus or minus the square root of b squared minus 0. Plus or minus the square. So that's b, isn't it? So that's the numerator simplified already to some degree. All over 2a. Because if you think I'm doing the whole lot of that. So we've got 0 as one of the axes. Because as Jed-Levi proves, minus tan theta plus tan theta is 0. So we've got one of the zeros already. And if you look at the graph, we can do it that way. So we just need the other one. So we need minus tan theta minus another tan theta. So what we want here is, for our second solution, We're only going for the second solution now. Minus 2 tan theta over A. Okay, well that's cool. That's also equal. Let's do it the easy way. 1 over A times minus 2 tan. So let's just... theta. Let's... over 2A. Indeed. Ha! That makes it even simpler. Those 2's cancel. Thank you. Those 2's cancel, so those 2's cancel. So it's actually minus 1 over A. 1 over A times minus tan theta. Way nicer now. Flip A upside down to get minus 1, to get 1 over A. To U cos theta squared over minus G times minus tan theta. Minuses cancel as well. So x now seems to equal 2u squared. I'm going to distribute that squared. Cosine theta squared. I'm going to make tangent theta into sine and cosines. So that over G times sine theta over cosine theta. Of course, that's all a multiplication, so let's carry that bar. Cancel that with that. 2 cosine theta sine theta. That's sine of 2 theta. We've seen that before. So that is 2 cosine theta sine theta is... well, let's put the u squared at the front. Let's say sine of 2 theta over G. Wonder where we've seen that before. I wonder where we've seen x equals u squared times sine of 2 theta in our case over G. Funny that. Looks like the maths works out. So, we've just done 2 ways of doing that. And we've now got answers that if you just plug numbers in, we know the height of the... we know how high this hill is. We know how far it goes. We could even start plotting x and y values and getting those answers. That's interesting. So let's go back to 20 meters per second and 45 degrees. And then we've got answers. Does anyone want to see me try and learn to use no limits quickly? As in, see if I can work out where the force stuff is. Let's see if I can also help with that green screen jump mildly. Yes, right, okay, so we've got a park. Let's build a new coaster. Let's call it Zero Goof. This has been so much fun, you miss hard maths. Looks like I'm going to have to do another stream another time on banking. So that's going to be the more physically based one. So let's say we've got Zero Goof. I want to play with the track on that. I want to grab the start vertex. I'm going to put it somewhere. And this looks like a top view to me. Just start sticking some tracks in. Let's select them all. Let's see if there are options here for something like make straight or whatever. Make straight 2D, make straight completely. Let's say that that is going to be section type. Can I just grab from, say, there to there? You're really going to do that, aren't you? Station. Why? Why are you not going to segment this? Okay, let's delete a few of these. Let's do it this way then. So let's say we're going to make you're going to be the station. I could even do with knowing what kind of coaster this is. Coaster. Oh, come on, give me a type. Type settings. Oh, God, no, that's complicated. Style settings. Oh, God, that's not good. Coaster. Oh, you've got style separators. I see, and type separators. Okay, so we'll then do... I see how this goes. Okay. We can do this. So it's going from there. Alright, that's... And then type separator can go kind of there-ish. Oh, it's not what I wanted. See which direction this is going. Let's have a look from the front, shall we? Okay, you're going kind of in the right direction. That's fine. I can work with that. Then this bit of track, let's just say that this bit is going to be a launch. Transport's going to be close enough, isn't it? Still wish I knew how to decide what this type was. Let's have a look at what it's decided it wants to be. And again, this has got multiple cars, so... Oh, hello. Ah, that's not what I wanted to say. Oh, yeah, of course. Because there's perspective on this. Let's unfreeze it. Let's not care too much. Why do I not get to find out what... Oh, coaster properties would help, wouldn't it? Figure it out. So we're not going to go classic anything. Let's say there's the Infinities. There's... Actually, what we used was a Eurofighter in Planet Coaster. Let's use a Eurofighter again. Might as well. Mode, shuttle. Physics model, meh, that'll do. Trains, one train. One car. Thinks about right. You've never seen this. Right, this is No Limits, Minxie. This is where things are about to get fun. Because what I can do in this is actually follow the plots a bit better. So that's going to be... And we'll play about with this. I'm going to say that you are going to be... Right, kilometres an hour. What is 20 metres per second in kilometres an hour? 20 metres second in km/h is 72. Okay, I can do that. We'll do 72. We'll say that you're going to be a limb. Why not? And you're going to go... Where? What's happening there? delete that. That makes more sense, doesn't it? Okay. So let's say that the station doesn't have to be long at all. That is definitely going to launch far enough. And then if we play and add a vertex, why are you so... Why is this game forcing this? Can I not say, oi, you don't have to be... I've already said your shuttle mode, haven't I? So why is this forcing a loop everywhere? We can see a G-force cone. We can see the speeds change, so the speed doesn't... this doesn't really need to be as long, so let's... just to give us a shorter launch. Oh yeah, we can add formulas. Ooh! Actually, that could be fun. Oh, we've got to work out how to do this. Oh, we're going to learn how to do formulas in this. Haha, I can have fun, yeah. I wonder if anyone's done a zero-G formula. I don't know. Doesn't look like it. And there's force vector and there's special track. Oh, I'm going to have fun learning this. Just need to know how to stop you forcing full circuit. Help. Tutorials. Use okay. Back. Reference. Actually, I think it's more to do with setting the start vertex. So what happens if I do that? Okay, I know what's going on here now. Right. Ignore my idiocy. What's actually going to happen is that kind of thing, and we need to now, because this is spline based, we need to make this bit straight, don't we? How do we... There was a tutorial on this. Would you believe there was a tutorial on making straight track? Let's see how we do it. Requires a couple of vertices. Oh, you enable the straight... Okay. So double click you. Strict. Cool. Double click you. Okay, you're already strict. So at this point, we can get you at about that angle. Can we prove that that's going to be the right... How do we get that to be exact? I'm having too much fun here now. Am I allowed to have this much entertainment? I'm just wondering if we can actually put the equation in here and make a proper zero-G hill. New formula. Number of roll points, however many. Help. Right, what do we need to do? What's the language? So, length. Okay, so we've got X's and Z's. Remember that L is at 9? Yes, but I'm having fun now. 10 metre long straight. X, Y, and Z of output positions T is the time. Oh, time goes from 0 to 1. Okay. So I want to know what my directions are. And this is in X's and Y's. Ah, forgotten you can't scroll there. So you can do X, Y, Z. T is the loop time, is the time. So actually, we need to go back to a what's it, don't we? Actually, we don't, because we can do something else here. We can go. Well, what was the solve on this? Because we can go X equals, and how did we solve this? We solved it with this. What happened to G, U, and V? Right, G, I think we can stick it. We're going to have to use actual numbers here. This is where we go back to using actual numbers. Have we got any constants? EG is our G. So they've given us that. So X, and this is going to be all in terms of T. So T is going to sweep from 0 to 1 for this. So X is U squared, or what's U? Let's actually define them. U equals 20. We're saying that for meters per second. A for the angle is 45. Let's just check if this works in. It uses radians. Okay. 45 degrees in radians is pi divided by 4. Essentially, 2 lots of pi radians is a full circle. So pi lots of radians is half a circle. Pi over 2 radians is 90 degrees. Pi over 4 is 45 degrees. Those are numbers. I was hoping to avoid it, but hey, if we're going no limits, we're going to have to go with it. So there's your U, there's your A. So what did we say X was? So X is U squared. Okay. Times the sine of 2A. What's going on? Times the sine, and it's going to be caps, I reckon, of 2 times A. Have I got to put that there by any chance? Tell me I've got power. Oh, power is that way. Do you know what? U squared is U times U. So that all over G, which we're using their version of. So that is as far as it goes in the X direction. And to do it parametrically, we'll do it times their time, which goes from 0 to 1. Trying to work out why there's a thing there. Let's go from the top. Okay, so that's. They've defined X in that direction. Alright, we're going to change it. We're going to use their Z direction. Actually, no, we'll use X because we can grab an element and rotate it anyway. And it would be Y, I think, would get us that other direction. No, Y is up and down. Okay, so and Z is going a different... Okay. X is that. Z is 0. We're going to say that Y is then this whole nonsense. So let me put it on the other screen just so I don't have to keep flicking backwards and forwards. Oh, he would. He'd be an utter heaven, I'm sure he would. So Y is X times tan of A minus EG times X times X. And then that can all be over 2 times... Well, we'll use the power thing there. U times cosine of A raised to the second power. Unknown pow because it's PWR in this. And what we have here, I think, if I view from one side or another, is why is that all been rolling and silly? View from the front. I don't understand. Oh, yeah, no, it's with relation to X. Let's view it as a. Hang on. I wonder if we're looking at having to do these as capitals. I don't think we do. It hasn't suggested that. Hmm. So why is it so? Let's have a look at the perspective view. What the holy moly is that? Really? That doesn't make sense. So that is in radians. Number of generated roll points, 100. Okay. 2. I'm not sure where I'm going wrong here. I'm very not sure where I'm going wrong because we've got gravity, which is that. Got it there as well. I mean, we will capitalise those X's as well. Don't know why any of this is going wrong. The current time output variable, so loop time is T. Well, we had X and Y as formulae before, didn't we? Let me flick back and get Y in terms of T instead of in terms of X. I didn't realise we were going to want that. No, my word, we've gone through some. So X is... Oh, of course, hang on. That's not at all what we wanted. Is it? Because that's the final. So, hang on, that's the fraction of X that we go to, and then that's... Yeah, let's do these back in terms of T, and we'll just scale T. So, time equals T for now. Let's not try and do this smartly. Let's then say that X is going to be U. Oh, hang on, it's in radians. No, we've done it in radians. So X, back to the very original, is U times cosine of A. Oh no, T is a different thing, isn't it? This could go really badly. Times T. Y equals... Try this way then. U times sine A times T so far minus 0.5 times EG times T times T. Well, these should all be time. And that should be time, because we're going to say that time equals... three of those. All right. 5 of those. Okay. U cos A times time, U sine A for the Y. Oh, actually, yeah, that would work. Okay, so that looks like a 0G hill to me. So I'll go up there and then back down. So it's really not going to take us too long. In fact, could we work out how long it would take to get from there to exactly there? Let's try 1.4 just to see. No, higher. 8. 7. So that would do it. Okay, so we'll create it as 0G for the heck of it. Why not? And then let's just see, can I go and into the track, go there and add an... can I just go and add the element? Oh, I've actually got to save it, haven't I? I have to save that as 0G. Okay, we can do this. 0G. We can get this. And then we go and add the element there. we can kill this off. There is actually another way we could have done this, but we'll show it. We'll show that as well in here at some point. And again, don't expect this to actually be the right way of doing it. I've now got to make that match up with that pretty much. So we're going to get jank at about there, but if we add a type separator about there, then we'll select that bit of track. We'll call you standard track. Oh no, we won't. We need to add the type separator there, if you would be so kind. That needs to be that transport type again. So we get the speed comb. Let's have a look at what the G-force comb says. So yeah, you'd spike there, but then that is really, really low. And of course, we can tweak this. I mean, that smoothing is jank AF. I don't know how we're going to kind of deal with that other than sort of, you know, let's just finagle it a little bit. Looks pretty smooth. But now if we change the speed of this, so if we go not style settings, type settings, I would imagine, I would say that, you know, let's try that at 80 kilometers an hour. So we're going to go over it at 50 mile an hour essentially. There's more G's there. And that's more negative G, because it's G-force going in the up direction. So this is the G-force cone. And every point on that, it's showing how high the G's are. So at the 72 that we were at, I think, yeah, it's minus fun amount. But we can tweak it. We can say let's launch a little bit slower. Let's say we're going to launch at that, because that's probably closer to 20 meters a second. Or we'll even launch a little bit slower. But whatever, that's 20 meters a second launch. That's the G-force comb. And obviously if we then add a vertex in like that, yeah, we're going to spike a bit there. So again, just try and gentlify it a little bit. That'll do. We'll add a vertex. Yeah, we're going to have horrendous G's. But the idea is I want this to just kind of not be anything. And if I were to sort of scooch that there. But we've got a decent 0G setup. Well, shall we save and have a ride and see what happens? I'm very much hoping that we've gone high enough now. Let's just make the track higher. I'm hoping that we get something close to 0G at that point. Let's save it. Or, you know, just Control S. And I think we can go into sort of park settings, whatever. How do we go into ride mode? We go leave editor. We click play. And somewhere around is, oh my word, why is that not whole? I know why that's not whole. I've fallen for this before. We freeze it first. And then we'll leave the editor, we go into play mode. We're in here. We'll pause that because I want to see the force displays. Can we see them? Trying to see if we can see, like, interesting stuff. View panel, F7. No, that's not good. Quick help, open help, show cursor. Well, let's go for that. Play mode. Things like, simulation panel. So we can see the forces. Now I can see them. Unfortunately, they're very, very zoomed out. But let's unpause it. Let's have a roll at the normal speed that it should go at. Up we go. 0 G's pretty much. And sort of going really slowly back. We see that it goes down to minus 0.3 over there. And that's all the way over. So that is No Limits plotting our 0G hill. Of course, we've done a lot of work, but we could also have done something slightly different. Let's unfreeze the track. Let's delete some vertices. Like back to there. And what we could do is add a force element. Somehow. I'm trying to think of how we do that. Why are you not giving me the ability to... the last vertex of a standard track has to be selected. Okay, so we'll just add a... We'll put the type splitter kind of there. We'll make you into standard track. Then we'll select that vertex. We'll go to element, force vector. Right, I don't know what they've decided to do, but what we're going to do is... Okay, we're not going to go through any of that. But I'm going to say for sort of 2 seconds, the start speed is going to be 72, something like that. The end speed can be whatever. We're going to clear the points, because actually what we want to do is drop to 0. So what's going on here? How do we make this actually do anything now? Does that kind of assume that it's gonna... Okay, I see. So can I stick a point in here? Because we've got no lat, no roll. Okay, so right click sticks a point in and takes one out. So I'm going to make it go pretty much straight to 0. Or pretty quickly to 0. And I'm going to try and make it hold 0. Just in this graph. By right clicking, adding a bit, moving it around. So the jerk to 0 is going to be interesting. But we can add, like, a bit more on. And what we've got now is a 0G hill there. Designed exactly the same sort of thing as that parabola. But we've used force vector design. So what that means, and I'm going to have to sort of end reasonably soonish just because, well, really, I can't be bothered fixing the green screen. But what that is we've said we want these forces. So I've said I want this to go to 0G and then stay there. And what No Limits has done is said, well, the way you do that is you go over this. And the way you go over this, you know, this force comb says that that's pretty much 0. Now, if we look at the speed comb, we're losing a bit and then regaining it. If we look at the radius comb single, you'll notice that it's not a constant radius. The parabola bit, it changes. Or the radius comb XY, or, you know, blocks, we're all in one block segment. And there's the spline again. Then there's none. So that's how No Limits does force vector design. Now, there is an outside tool that you can use that I know a little bit better than that. It's called OpenFVD or FVD++, and I need to not do that. I need to do it this way. Come on, Gareth, you know what you're doing. Many won't believe you, but you do. And again, you know, you can add geometric sections. If I were to load sort of something that I played around with not long ago, you can, you know, add, well, that's, interestingly, you know, you've got a loop there, so drop, because I haven't modelled I've just modelled it from the top of the left hill, drop into a loop, constant force, well, with a bit of lateral to do that, and then up through a 0G roll. Now, try and ignore the fact that it's rolling and just follow this line, and you'll see that that's again the parabola shape. It's just that we're rolling round it. By the way, 0G roll is a 0G hill with roll. Nothing more. So, you know, that track, edit, that force segment. If we just didn't add the roll there, that would be a 0G hill. So that was over 3 hours on 0G hills. I'm going to have to do another one of these, aren't I, soon?